In previous lecture, I discussed what is algebraic structure, semigroup, monoid group, and abelian group. If one binary operation is closure in that set, it's called as algebraic structure. If it is closure plus associative, then it's semigroup. If it is closure, associative, and identity, it is monoid. If it is closure, associative, identity, and inverse, then it's a group. If it is closure, associative, identity, inverse, also commutative, then it's a abelian group. Today I'll discuss some more example of it. Example 7, which of the following is not a semigroup? For semigroup, it should be closure and associative. Let's see the option. First option A, 1, 3, 5 till infinite with respect to multiplication. It is saying odd numbers with respect to multiplication. If we multiply two odd number like 3 multiplied by 5, it's 15. It's also odd. So I can say it is closure. Also it is associative as multiplication is associative. Hence it's a semigroup. Next option B, 2, 4, 6, 8 till infinite with respect to addition. If we are adding to even number like 4 plus 6, it's 10. It's also even number. Hence it is closure. Also it is associative as addition is associative. So you can say option B is a semigroup. Next option C, 1, 3, 5, 7 till infinite with respect to addition. So it's asking about odd number addition. When we add two odd number, it's a even. Like 1 plus 3, it's 4. 3 plus 5, it's 8. And 4 and 8 are not in this set. Hence, it's not closure. As it is not closure, so don't need to check for associative. It is not a semigroup. Even it's not a algebraic structure as it is not closure. Next option D, 2, 4, 6, 8 with respect to multiplication. Yes, when we multiply two even number like 4 multiplied by 6, it's 24. 2 multiplied by 4, it's 8. It's present in this set. Hence it is closure. Also multiplication is associative. That's why it's a semigroup. So for semigroup, we just need to check whether it is closure and associative. Next example 8. This set A, 0 less than equals to x less than equals to 1 and x is a real number with respect to multiplication. So it is saying this set contains all the real number between 0 and 1. Binary operation is multiplication. And there are 4 options. So just check, is it closure? Yes, it is closure. When you multiply two real number, we'll also get another real number and that will be between 0 and 1. It is also associative as multiplication is associative and it also have the identity. Here it is less than equals to, so 1 is included, right? So we have identity, closure, associative and identity. Is it have inverse? Suppose for 1 by 3, its inverse will be 3 by 1, right? 1 by 3 multiplication 3 by 1, then it will be the identity 1. This 3 by 1 is greater than 1, right? So it doesn't have inverse that belongs to this set. It is closure, associative and identity. So you can say it is a monoid but not a group as inverse doesn't exist. So answer will be option B. It's a monoid but not a group. For group, inverse should be present. Next example 9, let Z equals to set of all integers. Now A star B equals to minimum of AB. So here binary relation is minimum of AB. Then Z star is dash. So you need to check further. This is algebraic structure, semigroup, monoid, group or abelian group. It is closure as Z contains set of all integers. Also it is associative. Now check the identity. Suppose 3 star 5. Then minimum is 3. Then 3 star 7. Minimum is 3. So if you are taking any larger number, you are getting the minimum as same number. But is this unique? No. That should be unique identity element. But here we can take any larger number, we'll get the same number. There can be identity, but as it is not unique, so we'll not consider that. So this binary operation is closure, associative, but no identity. As no identity, we don't need to check the inverse and commutative. So we can say it's a semi-group, right? Next, I will discuss finite group. If number of elements in a group are finite, then it's called as a finite group. Till now, we discussed all are infinite. Next, we will discuss finite. And order of finite group equals to number of elements in that group. If a group has only one element, then that element is the identity element of that group. Like S equals to 0 is a group with respect to addition, and S equals to 1 is a group with respect to multiplication. As in case of multiplication, identity element is 1, and in case of addition, identity element is 0. S equals to 1 minus 1 is a group with respect to multiplication. We can make a table like this. This is multiplication. Here you can write 1 minus 1, 1 minus 1. So 1 multiplication 1, it's 1. 1 multiplication minus 1, it's minus 1. Minus 1 multiplication 1, minus 1. Minus 1 multiplication minus 1, it's 1. So you can see all are in 1 minus 1. Hence, it's a finite group. And it have the identity. Identity is 1. It also have the inverse. For 1, inverse is 1. For minus 1, inverse is minus 1. So by which number you are multiplying, that you are getting the identity element. Here identity is 1. Let's say another example. Example 10. The cube root of unity 1 w square is a group with respect to multiplication. Let's create a table like this. Here it's multiplication 1 w square, 1 w square. WQ equals to 1. Just remember this. Now 1 multiplied 1, it's 1. 1 multiplied w, 1 multiplied w square, it's w square. Then w multiplied 1, it's w. W multiplied w, it's w square. W multiplied w square, it's wq, and wq is 1. Next w square, then w square multiplied w, it's wq equals to 1. Next w square multiplied w square, it's w power 4. We can write w power 3 multiplication w, and this is 1 multiplication w is w. So we can write w here. All the multiplication results are 1 w square, hence it is closure. Also it is associative, as multiplication is associative. Is there identity element exist? Yes, 1 is the identity. By multiplying 1, we are getting the same result. Is there inverse exist? Yes. In every row there are 1 present. By multiplying which element, we are getting the identity element, that is the inverse. Like for 1, 1 is the inverse. For w square is the inverse. For w square, w is the inverse. When we are multiplying w square with w, we are getting 1, right? So it is closure, associative, identity element exists, also inverse exists. Hence, it's a group. Let's see another example. Example 11. The fourth root of unit 1 minus 1, I minus I is a group with respect to multiplication. We can create similar type of table. Here will be multiplication 1 minus 1 I minus I. Here 1 minus 1 I minus I. I square equals to minus 1. Just remember this. Now 1 multiplied by 1, 1. 1 multiplied by minus 1, minus 1. 1 multiplied by I. 1 multiplied by minus I, it will be minus I. Then minus 1 multiplied by 1, minus 1, 1. Minus I, then I. Then I multiplied by 1, it's I. I multiplied by minus 1, minus I multiplied by I, it will be I square is minus 1. Then I multiplied by minus I, it will be minus I square, so 1. Next minus I multiplied by 1, minus I. Then minus I multiplied by minus 1, it will be I. Then minus I multiplied by I, minus I square, it will be 1. Minus I multiplied by minus I, it will be I square, it's minus 1. So this is our table. All multiplication are in between 1 minus 1, I minus I, hence it is closure. It's also associative, as multiplication is associative. It also have the identity element. Multiplying by 1 we are getting the same result, hence 1 is the identity element. It also have the inverse, as in every row identity element is present. So here for 1 inverse is 1, for minus 1 inverse is minus 1, for I inverse is minus I, for minus I inverse is I. So this multiplication is closure, associative, identity and inverse, hence it's a group. We can also do addition module and multiplication module. Here m is a positive integer and let's consider a, b are some integers. Now addition modules. Addition module we can represent by this symbol, plus surrounded by a circle. Here we can write the module. So a addition module mb equals to ab if a plus b is less than m, else it will be remainder of a plus b division m if a plus b is greater than equals to m. Next is multiplication module. So multiplication module we can represent by this multiplication surrounded by circle. Here we'll write m. If a multiplication b less than m, we'll write simple a multiplication b. If it is greater than or equals to m, then we'll write remainder of a multiplication b division m. In next lecture, I will discuss some examples of addition module and multiplication module. Today, I discuss some examples of groups and what is finite group. If this lecture is helpful for you, please like, share and subscribe. Thank you. Bye-bye.